We're going to start our first section, which is 11.1. It's about vectors in the plane. So we're going to start with the definition of what a vector is. So a vector is a quantity that has both magnitude and direction. So the classic example that you should think of here, think of force. So for example, if you apply a force to move a box across a room, the force you're applying there is an amount, how much force you're applying, a magnitude, but there's also a direction that you're using to move that box. So visually, the way we represent vectors are with these arrows like this, and vectors always have a starting and an ending here. So I'll say A and B. A is called the initial point, and B is called the terminal point. And the way we're going to notate a vector, if this vector, I'll call it V, you can write it with an arrow across the top. Or if you know the initial and terminal point, AB, you can write AB and an arrow going from the initial to the terminal. Now I do want to mention one quick note here. Note that the zero vector has length or magnitude 0, but no specific direction. So for example, if you're applying no force, there's no direction you're applying that force in. All right, so we know what vectors look like. One of the first things we're going to talk about is what it means for two vectors to be equivalent. So definition, I'm going to say vectors U and V are equivalent if, well, remember vectors are described by length and direction. So they have to have, if they have the same length and direction. So let me kind of show this in a diagram here. Let's say I have this vector here with initial point A, terminal point B, and then I have another vector with initial point C and terminal point D. If these two vectors have the same length and they do look like they have the same direction, I would say that they were equivalent, and we use an equal sign to denote that they were equivalent. All right, so let's look at an example. And let's show some vectors are equivalent. So let's say V is going to be represented by the directed line segment from the point 0, 0 to the point 3, 2. and I'm going to use U for the directed line segment. From the point 1, 2 to the point 4, 4. And what I want us to do is show that V and U are equivalent. So let's plot these two vectors here. So the first one goes from the origin to 3, 2. So here's my vector V. And then my vector U goes from the point 1, 2 to the point 4, 4. So the first thing we want to do is show that these two vectors have the same length. They might not look so nice in this picture, but we want to show that they have the same length. Well, really, what you're doing is you're measuring the distance of that line segment, really the distance between 2 points. So we're going to use our distance formula. The distance is the square root x2 minus x1 squared plus y2 minus y1 squared. So let's use that formula to find the magnitude of U. Let's start with the magnitude of V. The magnitude of V (3 minus 0 squared plus 2 minus 0 squared). This is the square root of 13. If I compute the magnitude of U, the square root of 4 minus 1 squared plus 4 minus 2 squared. It's also the square root of 13. So notice here that these two values are the same, which means these are equal. These two vectors have the same length or magnitude. Well, now what else needs to be the same? They need to have the same direction. So here you can think of direction as being the slope of the line segment. So I'm going to look at the slope of the vector V, and remember it's rise over run. It's going to be 2/3, and the slope of U is 4 minus 2 over 4 minus 1. It's 2/3. So again, these two values, these were equal, and what it means here is that these two vectors have the same direction. So I can now conclude that these two vectors, V and U, are equivalent.